right, let's get started. So last time we left off just at the tail end of backpropagation. I think I was rushing through it and I might have misplaced a variable here and there. So let's start, let's give a quick refresher where we were there. So this is just backpropagation details. So just for context, again, I'm just going to simplified version here. We imagine you've got a multi-layer perceptron with some input, followed by a layer 1, and then a layer 2, and some number of layers. I'll say a layer k plus 1, then finally layer n we'll call the output layer. And all the intermediate layers referred to as hidden layers. And every unit, every neuron in each one of those layers is described by the function O. I'll call it, I think last time I did Y, but there's a lot of Y's and O's and A's coming around. So I'm just going to make it O to keep it a little cleaner here. So I'll say it's O. Maybe I'll move it down a little bit here. O, J, K. And so this is the output of neuron or node J on layer K. And that is going to be equal to the activation function there, taking as an argument this sum where I'll go from 0 for the bias term all the way to R of K minus 1, where this thing here is the number of nodes in layer K plus or K minus 1, so the preceding layer. And that will just be the weighted combination of those. So then I'll do W, L, J, K, and of O, L, I think, K minus 1. And so this thing here, that is the weight in layer K from node L in layer K minus 1 to node J in layer K. So in my convention here, the subscripts here, I've got it kind of like from to. So L is the earlier layer and J is where it terminates. And so the second subscript corresponds to the superscripts layer. So J goes with K and L is from the layer before in this notation. And then that same output here. And so that's just, I'll put a parentheses around here, and then this guy here is just output from node L in layer K minus 1. And just to be helpful, this stuff that's in the argument here, I'm going to call X, J, K. And I'll just define that as that same exact sum from 0 to R K minus 1 of W, L, J, K, O, L, K minus 1. Okay, so a lot of variables tied around there, but it's just supposed to, and I guess I could maybe just for clarity here, this is the activation function. On node J in layer K. And I think that's about everything there. So that's just a summary of the structure of the neural network for any particular node. This will hold, whether it's a node on the output or any of the hidden layers and so on. And so potentially a fully connected neural network, or fully connected layers in this multi-layer perceptron. So pretty general. So any questions about this is pretty clear. This is just the activation function on each neuron. And our task is to try to figure out how to use gradient descent to train all these weights. And so what we're going to do is we're going to calculate, so for gradient descent, then basically we've got a vector of all our weights, say in time t+1 is going to be set equal to the vector of all the weights in the step t minus some, I'll call it sigma maybe. Well, I don't want to call it sigma. I'll call it s for step size times the gradients with of our loss function, which I'll call E, with respect to this theta. So these are all the weights at next step. These are current weights. And this is a step size or a learning rate. And then these here are the gradients. And by the gradients, I just mean that this is going to be equal to a vector where it's just partial the loss function with respect to each of these weights, whatever it ends in, M, N, or whatever. Okay, so the goal here is to find a way to calculate all of these partial derivatives. So the loss function that we only see kind of at the end of the neural network after everything's calculated with respect to each one of these weights. And this will tell what contribution that weight has to making the loss function smaller. And so if we know what that contribution should be, then we know that, well, if we increase this weight by a little bit, it'll make the loss function smaller. If we decrease this weight by a little bit, it'll make the loss function smaller, and so on and so forth. Where our loss function here, we're going to say is just going to be 1/2 times the square of the error. So if the output is if the output of the matrix or of the neural network is, I'll say ON. So it's just the output of the last. It's the output here is just, if I assume the output is just a single value, which is just the output value of the neuron in the output layer. So it's just ON minus whatever I want it to actually be. So our desired output here. So this is our desired output. And this is the approximation. And if I have multiple data points, then I can sum all these things up together. And then if I have multiple outputs, I can also do that as well. So this is kind of the simplest case broken down from only considering a scalar output. So it's like a simple regression problem where, I could, if I've got an input data, so I've got some feature vector X and it corresponds to a single output. Then I've got another feature vector X2 corresponding to another output Y2 and so on. And you could add all these things up together. I'm just because they all sum, I'm just focusing on what we do with one data point. And so we're going to say, what is the partial derivative of this loss function? How do we make this loss function as small as possible by tuning these weights? That's what we're doing here. So this looks pretty ugly. So it seems like it might be intractable to calculate all these gradients. But it turns out that the structure of this multi-layer perceptron makes it pretty easy to calculate all of these gradients. It looks a little ugly, but at least for a computer, it's really easy to go down through and knock out all of these. And what we're going to see here is that they'll actually be able to calculate gradients at the output layer just using the error. And then from there, calculate gradients at the next closest layer. And then from there, calculate gradients at the next closest layer, all the way back. And so eventually you get all the gradients of all the weights. And once you have all the gradients of all the weights, then you can calculate this step here. You can do your gradient descent step, which will allow you to change all the weights. And once you've changed all the weights, then you can go back forward through it and calculate a new output. And that new output will generate a new error. And then you can go back and forth and back and forth. And that's what backpropagation is. Propagating error backwards, evaluations forwards. So it's kind of like error goes back, and then you do a gradient step. Evaluation goes forward, you calculate new error. Error goes back, gradient. Evaluation goes forward, and so on. So that's what we're aiming for here. So how do we calculate those gradients? Are there any questions about any of this, about the general framework here, what we're trying to do? Why do we care about the gradients for these weights? Okay. So the basic idea here is we'd like to calculate partial E with respect to just some generic weight, which I'll call IJK. I'll make that a little clearer, it's a W. And in order for me to do that, I can actually break that up using the chain rule from calculus. And so the chain rule here, I can say, well, in order for me to calculate partial E, I can actually break that into saying what's the rate of change with respect to kind of the position of the activation function. So I'll say what's actually partial A JK. And then what is the rate of change of the activation function with respect to its argument? And then finally, what is the rate of change of its argument with respect to the weight I actually care about? And if I look down through these, this one here is really easy, because if you remember, X of JK is just the weighted sum of all the WIJKs times, so if I flip back here, I'm referring to this X here. And so if I rewrite, in fact, maybe I'll just do that so that I don't mess up any of my notation. So I'll just copy this thing out. Actually, this thing here. All right, that there. Try to get rid of this thing. Okay. All right, so that's my X. Now, if I look at this X, if I'm taking the partial derivative of this X with respect to this weight, then pretty much all that I'm going to get, any weights that aren't that weight are going to drop out because they're just going to be constants. I'm taking the derivative with respect to them. So this whole element here is just going to become the output. So it's just going to be this thing here. So this partial derivative here is just going to be O of I k minus 1. Or in other words, it's the output calculated at the previous layer. So remember, all the layers are counted this way. And so that term there is just the output calculated at the previous layer. And so if I can just put as a reminder, this is just A I k minus 1 of xik minus 1. So that's easy to calculate. So then this middle term here, well, that's just, it has nothing to do with the weights or anything like that. That's just the curvature of the activation function. That's just the derivative of the activation function. So this, I could write, it's a little ugly, but I could write this as like AJK prime. So it's just the derivative of the activation function. So slope of activation function. Evaluated at this x bar. And then so all that I'm really left with is this bugger here, which is going to differ depending on whether it's the output layer or the hidden layer. So this, so maybe what I'll do is just say that we're going to take this thing and we'll say differs, and I'll put it on the next page, between output and hidden layers. So I'm going to have two cases. So that's really the key thing that I need to calculate, partial E with respect to partial AJK. So if I go and I do that, so partial E with respect to partial AJK, then maybe I'll move this in the middle of the page and then turn this into a cases block. Then up here, if we're in the output layer, then this is going to break down into just the air. So if I remember that my E is equal to 1/2 AJ, well, yeah, I'll call it AJN because it's the output layer, minus, evaluated at, the x's, minus the desired output squared. The partial derivative of this thing with respect to this thing is just going to be the air. The 2 is going to come out front, cancel the 1/2, and I just get the air. So this just becomes AJ in XJN. So the output of the neural network minus that. So this is the error of neural network. So then what about if it's a hidden layer? That's a little more complicated, but it's still something that we can pick apart. So, so I'm going to put a little line here so that it's clear that I'm separating these two cases. It's not really standard notation, but hopefully that helps. Maybe I'll put it in a different color as well. So if it is the hidden layer, then we can break it up using the total derivative. So what I mean by that is I can say it's actually equal to partial E partial X, and I'll do, sorry, I'm into sum. So the way the total derivative works is if you have a function that has a bunch of arguments and you're taking the total derivative of that function with respect to something else, like time or whatever, what you can actually do is you can sum up the derivative of that function with respect to each of its arguments times the derivative of the arguments with respect to the thing you actually care about. You can add all of those contributions together, and that's the so-called total derivative. So it's like the partial derivative is just one of them, and the total derivative kind of adds them all up together. So in this case, the total derivative I can take from, because I'm not worried about the bias layer, L equals 1 to R. In this case, I'm looking at the next layer behind it, K plus 1. And I am going to take the partial derivative of E with respect to, I'll do the partial derivative of X, L, k plus 1, and then the partial derivative of x L k plus 1 with respect to the thing that I actually care about, the partial derivative of a j k. And this here is the total derivative. And just making sure that, again, I don't screw up any notation like I think I did last time. And then that, this here can be further broken up by the chain rule. So this thing is going to equal to partial E, and I'm going to take it, I'm going to break it up down by A L k plus 1, partial A L k plus 1, broken up by its partial X L k plus 1, and then I left off with whatever's up top there already. All right, so this is another key point, is that we were able to break this thing up into these three factors summed over all of these nodes. And so each one of these things we actually have a handle on. So if I look at each one of these things, like this one here, if I think about x at node k plus 1, it's just the weighted combination of outputs from the previous layer. With outputs of the previous layer are these activation functions. So this thing here is going to just be a weight. You know, specifically, it's going to be WJL k plus 1. The weight in layer L from layer J, I'm sorry, the weight on node L in layer k plus 1 from node J in the previous layer before it. So that's just a weight. This thing here, that is just the rate of change of the activation function. So using that notation I had on the previous page, I can say this is just A L k plus 1 prime. So it's just the derivative of activation function. And this, by the way, is why to use backpropagation, you really need differentiable activation functions, because it really depends on calculating these derivatives. So this is the reason why in modern deep neural networks, you don't see a lot of threshold activation functions, because you can't get backpropagation through them because you can't calculate this derivative. Now, there are some activation functions like rectified linear units that technically aren't differentiable, but they're a little milder. And so you can still make backpropagation work. But generally, you need something that's mostly differentiable in order to make backpropagation work, because you have all of these derivatives of the activation functions hanging around. And then finally, this last term, which might look familiar, this term here, this is actually known from previous layer. In other words, if you look at what I'm calculating here, I'm calculating partial E with respect to the activation function for layer K, and it's using the partial E from the activation function from layer K plus 1. Well, in the previous iteration, I calculated this. So if I were to imagine, so like if I start, this is kind of, you know, this is like it's like an inductive sort of proof here. If I start at the output, I'll calculate this, and then I'll be able to use this in that place as I go to the first hidden layer. And that will allow me to calculate this. And then this one I'll be able to use in the second hidden layer, and I'm counting back from the back of the neural network. So from the output forward here. So from once I know the output, I can propagate that back into calculating the gradient in the first layer next to the output, and then I can use that to calculate the gradient in the next layer back from the output, and so on and so on. So it's a little ugly to write out, but the reason I wrote it out here is I'm hoping you see that in principle, all of this is doable. You could write a little algorithm that could iterate through all of the variables in a neural network. And is you would, starting with the output layer, you would know everything to be able to move all the way back through all of the hidden layers until you got to the front of the neural network. And at that point, you calculate all your gradients, then come all the way back to calculate a new value, which you could calculate a new error, and then repeat the process over and over again until you converge to some good weights for your neural network. And that's kind of the essence of backpropagation. So I could summarize in my notes, I've got these kind of compressed down, but I don't think, unless somebody really wants to see it, I hope you can kind of see, like we could we could simplify some of these things and write them all down, but I don't really care about you memorizing the formulas for backpropagation. They're easy to find, and there's vectorized versions that are more compact. But I just hope that you can at least see that in principle, backpropagation provides a simple way to calculate all of the gradients of all of the weights in an arbitrarily sized network. And that process would look, again, I drew this kind of virtually before, but you could calculate the error, which again would just be A in, what was my notation? Yeah, A in J, X in J minus Y. So we calculate that error, and we take it, and then we go backwards, and we calculate gradients. And then once we get all the way through the network, then we do a gradient descent step. And then from there, we now have updated our weights. And so we now evaluate neural network with new weights, which generates a new output. So there's a new error. So again, that's just AJN, XJ minus Y. And then we can repeat the process. So we go back and forth and so on, all the while, hopefully reducing error. So a little arrow kind of pointing down this way. And that's gradient descent on neural networks. That's backpropagation. So any questions about that? About the general idea behind backpropagation? Allows us for any, at least at this point, all I've said, for any feed forward artificial neural network, of arbitrary complexity, in principle, you can do this. In principle. Questions online? All right. Now, I say in principle you can do backpropagation. It's not practical for all networks in reality. So one of the problems, if you consider a fully connected, like, I mean, imagine you've got a neural network looking at an image, a very simple image that's, I don't know, 128 pixels by 128 pixels. And each one of those pixels has 3 color channels, red, green, and blue. Your input layer is going to need to be connected to each one of those pixels and each one of those color channels. So you're going to have a lot of data on the input, right? Just 128 times 128 times 3, right? So that's a lot. Now imagine you've got multiple layers and they're all fully connected. So every layer is fully connected to every layer in front of it. That is a whole lot of connections. And so each one of those corresponds to a weight. And if you've got multiple layers, they're all fully connected that way, then you just get a huge number of weights. And what ends up happening is sort of the gradient gets sliced up as you move back from the output, so that you get this vanishing gradient problem where the contribution of the weights on the close to the inputs stop sort of showing up on the output to a point where gradient descent can actually make useful progress. That's one of the things that can happen here. And so, and just in general, I mean, like any optimization meta heuristic, whatever it's gradient descent or genetic algorithms or whatever, as the number of weights gets larger and larger and larger, it just becomes harder and harder to find that optimal set of weights. And so ideally, we do not use these fully connected architectures where every layer is fully connected to every other layer. Instead, we introduce other architectures that you may have heard of before, like convolutional neural networks. So, so far, we've been talking about MLPs, which are multi-layer perceptrons. Now, you can then regularize those to sort of reduce the maybe number of weights or reduce the space of weights that you search over. And one of the ways you can do that is just by eliminating a lot of those weights. And that's what a convolutional neural network does. And so there's this, and it was bio-inspired itself. So a subset of those includes the convolutional neural network. Or CNN. And a convolutional neural network was inspired by the vertebrate visual cortex. And so in vertebrates, in the visual cortex, it's sort of this, it's kind of this, it's really kind of like a stack. There are these modules that connect together. Sometimes they're numbered. So they talk about like V1, it connects to V2 and so on. And so there's these kind of submodules that are connected together where the input from the eye goes into one, and then it gets processed down, a little bit like a multi-layer perceptron. But what was noticed was that there are, if you look at the receptive fields, remember that from radial basis functions. So you can look at the receptive field in each one of these. And basically that corresponds, if you look at like what neurons are activated when, so if you've got somebody staring at a particular image and they're not blinking their eye, they're not moving their eye, but something changes in the image and just one little spot in the image. And you can see how much of V1 responds to that. And what you find is that in V1, the receptive fields are fine-grained. So what that means is that if something in the visual field sparks, a very tiny element, then you'll get a couple of neurons, just a small number of neurons, one that'll fire very strongly and maybe a couple around it that won't fire that much. And if you move the spark over a little bit, then you actually get another set of them that fire, but a small number of them again. So they can track fine-grained details, and they actually build in V1 a map of the space. And so if you were to sort of drag a fine-grained object, fine-grained light in front of someone's eyes, and then watch the activation patterns that it's going on their brain in V1, you would see the exact same pattern being etched out like an Etch-a-Sketch in V1. And so these receptive fields are fine-grained. Now in V2, they are more coarse-grained. And what I mean by that is now, if that same little spark is going to light up a larger set of this map. And so what you end up finding is that as you get farther and farther back, then the receptive fields get kind of coarser and coarser. And so this general idea inspired them, I think, so my background's in electrical engineering, and so convolution is something we use all the time in signal processing. So I have to imagine that that the people that came up to this were sort of mildly inspired by the visual cortex, but probably really were leaning heavily on their signal processing background. You don't actually need the visual cortex to really come up with a CNN. It's kind of like people say special relativity and general relativity. Einstein's the only one who could have come up with general relativity, but some idiot somewhere would have come up with special relativity eventually. And I think some idiot somewhere would have come up with a CNN eventually. They might have named it something different, and they might have not been inspired by biology. But whoever did, come up with it first, at least thought they were inspired by biology. But it's just such a weak connection. I don't buy it. But that's the story, is that it's inspired by biology. And so So the way a CNN works is you can organize these layers so that you can create receptive fields so that the layer connected to your inputs is really not paying attention to every input. It's just paying attention to a small subset of that. And it can filter those layers. So that's one of the things that convolution does, and I guess I should mention that. So there's this, how many people are familiar with convolution? Okay, so it's all right. So then the boxcar interpretation, does anybody know what I mean by that? So I mean, convolution is this idea that you can have these, I'll call them kernels, which are these small stereotyped patterns. So we'll say these small, I'll just call them small patterns that can sweep over a signal to filter it. And so the idea here is like, let's say I've looked at an image and it's got a bunch of square features on it, like really sharp edges or whatever on there. And you want to get rid of all the sharp edges. And so you go into like a program like Photoshop or whatever, and you apply a filter. And that filter looks for any time it sees a sharp edge, like this one, it will then turn it into a round edge. And how does it do that? It can simply average all of the pixels. So imagine there's some sort of box that is a small box, much smaller than the image, that of whatever, 9 pixels or something. And whenever it sweeps over 9 pixels, it returns the average of those 9 pixels. And so if you were to sweep it over this image, then you would end up getting maybe this line out here, but when it got to this corner, they would average in some of this white space, so this sharp edge might not look quite as sharp, and you would end up getting something that might be rounded out a little bit. And so convolution is the operation which takes these kernels and it sweeps them over these images and replaces it with a resulting image that is so-called been filtered. So this is a sort of a filtering process. And so it allows you to extract things that you care about. So in audio signals, you might have heard of like a low pass filter, gets rid of high frequency signals. So you only hear, like if all your noise is in the high frequency, it helps get rid of that noise. So you only hear the low frequency stuff you care about. It's kind of a similar idea here, where if you just care about the big trends, you might want to, if let's say you had a bunch of noise in this image here, an averaging filter might end up reinforcing the thick lines, but getting rid of all the random stuff so that when it comes out, all of that's gone. And so the way convolution works is it's just a weighted combination of points. Like, so each point is a weighted combination of points in this sort of receptive field. And that ends up in the output, that's what that gets replaced by. And then this shifts over. So you can imagine building a feed-forward neural network which implements convolution without any sort of dynamic sweeping going on into it, where basically you could say the first layer of the neural network just only looks at these 9, so you've got one node that's only looking at these 9 pixels. The node next to it is looking at the 9 pixels, shifted over one. The node next to it is looking at the 9 pixels shifted over one, and so on after that. So every node of that first layer could be calculating a pixel from this convolution operator. So you can implement convolution in layers. And so that's what the convolutional neural network does. And what's beautiful about that is, it definitely reduces the number of weights. And so the interesting thing here, I only need 9 weights. Well, so that means that, in the worst case scenario, each node is connected to 9 inputs. And now I only have to worry about training 9 weights per node. But I can actually go even further. And I can go into a convolutional neural network and say, actually, this kernel, I want this kernel to be the same for all of these nodes. And so I can then kind of make an optimization here where every single node uses the same weights. And so for that entire layer, I only have 9 weights that I have to train. So even though my input space is gigantic, the number of weights I have to train are relatively small. And these, by training these weights, I extract features that then downstream layers can process. And so I might be able to extract, there might be some useful pattern that I'm looking for here, like blue squares, blue circles or something like that. So I'm just looking for blue circles. Well, I will now have a blue circle node. So I'll know, is there a blue circle in the top right? Well, if there's a blue circle in the top right, I can then say, well, given that I've got blue circle in the top right and red circle in the bottom left, that tells me something useful about the image. And so in downstream layers, you can start building up higher order logic where you're actually now not just processing raw pixels, you're processing concepts and those sorts of things. And that's what's going on in a CNN is you've got these different filter layers. So convolution layers, so conv layers, and they are effectively filtering, or you could say extracting from one to the other. And so that's one thing that's going on here. The other thing that you've got, and if it helps, I mean, I could draw a little, I don't know if it's helpful to draw a little like, imagine they've got these little convolution kernels. I've got an image. I've got these little convolution kernels, and they're actually overlapping too, but I'm just not drawing the overlapping ones. And each one of them is mapping to a node in a hidden layer. So there's a node, hidden node, and it's calculating an output in a new image, which then can be processed by further hidden layers and so on. So that doesn't reduce the dimensionality like we see in V1 to V2, but it at least filters. So the other thing that you see in convolutional neural networks are so-called pooling layers. And in this case, they just reduce the dimensionality of the information. So the idea behind a pooling layer is I might have 9 neurons in the previous layer, but in the next layer, I might do what's called like a max pool, where all 9 of those neurons in the previous layer will be replaced with 1 neuron in the next layer, which is just the maximum value from previous kernel. Well, I won't want to say kernel, from previous layer. So I've got, in the previous layer, I've got a bunch of these 9s, and they all get mapped into a single node. And so by doing this, I can, downstream layers can be, you're dividing the size of these layers by 9 by replacing 9 with 1. And so that allows me to take a very high dimensional input. So high dimensional input. And then I can effectively filter it. So filter useful info, and then decimate it. So reduce size, so that now I have a manageable set of features. So now I may have gone from thousands of inputs here that I have to worry about to hundreds. And once I have this manageable set of features here, now I can apply fully connected layers to this. So typically the way these convolutional neural networks work is you've got a stack of these things. They keep reducing the dimensionality. They output a set of features, and then you pop on maybe one fully connected layer. Maybe that's all you need. And that fully connected layer, like I mentioned, these features are kind of extracting useful concepts. And so that fully connected layer is basically just combining these concepts. So, blue circle in the upper right, red circle in the lower left, all those end up getting combined into a classifier or whatever, classifier, linear regression, whatever, out of the end here. So this is often used for like image classification, like a black chair versus a white cat. And so, at this level, all it can see is black and white. But gradually, these convolutional kernels start to extract details that help you to assemble geometric shapes into cats. Like I know that cats generally look like this. I know that chairs generally look like this. They're usually the combination of these colors and these shapes and these graphical features. All that ends up getting combined in these downstream layers. Maybe you need a couple of fully connected layers to do that, but you might even be good just with one. And so, so this is your basic convolutional neural network. And one of the nice things about deep neural networks is they're modular. So what people have done is, and you've probably heard of some of these networks out there, like AlexNet was a very popular CNN, and there's a bunch more, ResNet, and many others. So these people have trained convolutional neural networks to be very, very good classifiers on large image sets. And then you can just take their CNN, pop off all of the output processing, and then pop on your own. So, and these often work for image sets that they've not seen before, but because it turns out most of the training happens in the fully connected layers. And so that you can get a CNN that's been trained off the shelf through many hours of work by some poor graduate student out there, and it now is a commodity. Because now it is an effective feature extractor. It can extract features from generic images. Now, those features, when processed in the original context of AlexNet or ResNet, might be like sword or something like that. Like they would end up being something that wouldn't make sense for your context. But if you shine images on this thing that even it hasn't seen before, you can then train your neural network to translate the features it produces into the classes that you want. So even though it hasn't been trained to recognize, I don't know, iPad pencil or something like that, you can maybe, without actually retraining any of the neural network, just by training the fully connected layers again, you can actually take the features it does recognize and put them back together in different ways so that you can recognize things your own. And that's what they refer to as transfer learning. So that's this idea that you can take a CNN trained to do one thing and repurpose it to do something else. And it turns out that it works pretty well at that. And so deep neural networks allow us to do that because they allow us to cut the layers up and put the layers back together. Whereas if we just had a single hidden layer, it's a lot harder for us to export a part of the single hidden layer. So that's another nice thing about these deep networks, the modularity. All right, so that's a CNN. Are there any questions about that? I see a question online. So the question, do you always have a convolutional neural network followed by a fully connected, or do you sometimes have scenarios where you could have convolutional followed by fully, followed by convolutional, followed by fully, i.e. do we have CNNs used in the middle of deep neural networks? If you actually go and look up like AlexNet, for example, you can see the architecture of it, and you can find that these what I'm calling convolutional neural networks actually often have got a little more magic in there. So a little more special sauce in there, which sometimes might mean that they might interleave a fully connected layer somewhere in there. Generally though, you're going to have the sparser the architecture is closer to the inputs, because the inputs are high dimensionality. And you don't really want to start playing around with these fully connected architectures until you've really reduced the dimensionality significantly. But certainly, when you train your fully connected layers, in theory, if it's a small enough fully connected layer, if a convolutional architecture is best, then it will find it on its own, if you've got a really good optimizer. So it's certainly realistic that you might have, effectively convolutions pop up. Like if it's really important for you to find frequency content in an acoustic signal, then, it's probably a good idea to implement a Fourier transform, which is effectively what's going on in a convolutional kernel. And so it might be that you end up implementing Fourier analysis without even realizing it because you just trained a fully connected network, or you might have that idea ahead of time, then that might be useful. So you decide to put a convolutional layer in here. So absolutely, there's a lot of flexibility. And so those of you who, I mean, if you started to play with this stuff using frameworks like, TensorFlow, PyTorch, et cetera, you'll find that, you can kind of just plug in whatever layers you want and whatever patterns you want. And then it's very empirical at that point. And then you just run them on benchmarks and see how well they do. So absolutely, there's no rule as to how you have to do it. But I would say that you generally want to keep the fully connecteds and the lower dimensional side of this path here. All right, any other questions? Yeah.
You mentioned the convolutions as a form of regularization. Can you elaborate on that?
Yeah, so this term, the question was, can I elaborate on how convolutional neural networks can be viewed as regularization? So regularization is a very overloaded term in mathematics and in machine learning. And all it really means is reducing the complexity of the optimization task so that you don't get stuck in a lot of like local optima and things like that. And so the convolutional layers end up they have a lot fewer weights, and that's basically it. So in this case, they just have fewer weights and they make the optimization problem easier. It may be that convolutional layers are not the right architecture. Maybe you've made a bad choice by putting the convolution here, but it just so happens that when that they tend to work so well, and especially in these image classification tasks, that people say there might be a better set of layers that we could put here, but these are darn good enough. So now there are other ways you can regularize the optimization process that are kind of outside of the scope of this class, but they all kind of revolve around, it's kind of like in PSO. Like I said, that PSO tries to hold the weights together. The major problem here, and I didn't say this exactly when we talked about PSO, is that there's so many weights in these deep neural networks that compared to your data, you're probably over parameterized. I mean, you probably have way more parameters than you have data. And that's ultimately the problem in all neural networks here. And that's what makes it in such a hard optimization problem. Because you have, say, 100 data points in a million weights, there's a huge number of ways that you can find a good input-output mapping that matches your 100 data points. You can fit those 100 data points perfectly and probably do it in multiple ways if you've got these million parameters. So what regularization really does is it just sort of reduces the accessibility of this over-parameterized space so that you don't get, your poor optimizer doesn't get stuck in traps. I know it's kind of abstract. Does that kind of make sense, or does that answer the question? Okay. All right, any other questions? All right, cool. So, okay, so usually I have, depending on timing, so I mentioned that the vertebrate visual cortex has this really nice structure that kind of looks like a convolutional neural network. I don't want to talk about it too much, but at least some of the work that I do in my lab is we actually look at the architectures that go on inside insect brains. And it turns out that what's kind of an interesting thing is that in an insect brain, if I just focus on olfaction, so smelling, then you've got these really complex odor signals. So it's like barcodes of odors. So whenever you smell, you get into the presence or absence of various different odorants, and the sensory system, especially in an insect, it's very highly tuned to these odors, produces this really complex image, scent image, that it's just as complex really as looking at a raw image. And so all of these inputs come into this, this structure called an antennal lobe. And that antennal lobe has these things called glomeruli that are scattered around it. And so you've got all these odor signals, I'll call. I'll just simplify this for time. Goes in. And what's kind of cool is that I have colleagues that you can open up the insect's head and look at their antennal lobe and all the glomeruli. And you can stain them with this special dye that lights up when neurons fire. And as you puff an odor in real time, you can watch these glomeruli, some will stay off and some will turn on. It turns into like a binary code. So, and some people call this the olfactory code. And so some of these turn on, some stay off, and so on. And there's a lot of cool things that happen in this olfactory code. As you start reinforcing these odors, so some odorants will end up getting reinforced like with a sugar reward. And so mixtures that include those odorants will start changing their olfactory code to look more like the pure odorant. So it's kind of like if you've got a mixture and you smell one sweet thing in it that really is rewarding, if you smell that one sweet thing alone, you get a certain pattern here. If you smell it with a bunch of other things, if that thing hasn't been rewarded, you'll get a different pattern. But once you've rewarded that one thing, gradually these patterns start looking like the other. It's like you actually, this one a neuropill, the antennal lobe, becomes a discriminator where it actually can tune into that. But I don't want to focus too much on that. What I'm kind of focusing here is this is this is effectively a feature extractor like a CNN. And what's cool then is that this then gets projected up to this thing called a mushroom body. And the glomeruli, there's like, maybe let's say, there are like, say, around 50 glomeruli. Depending on the insect, it's going to be a different number, but we'll say it's around 50. The mushroom body, each one of those glomeruli gets projected up into these things called Kenyan cells, of which there are around, say, 200. And so there are, I call projections, there are axons, basically, long axons, these things called projection neurons, that map random glomeruli to a set to these. Now, and so each one of these mushrooms, because remember, there's only 50 of these, and there's 200 of these. And so you're going to have kind of a multiplicity here in order to make that mapping work. And we know that this projection is random because you can actually take, say, flies that are isogenic. They're basically almost clones, and they'll have different projections here. So during development, they have different random projections. And then this mushroom body, these Kenyan cells, that ends up going out to these very simple neuropills, which actually end up driving motor activation and all that. And so I won't name those, but there are, we can call this actuation centers. And these are relatively small and simple. And then that ends up driving motor, et cetera. And so if you look at this, really what you've got here is a feature extractor like a CNN, and then a random projection to this kind of hidden layer that then has a decoder that's after it. So this is like a decoder. So you can think of this as kind of an output layer. You can think of this as sort of a single hidden layer. And then this is a feature extractor with random connections here. And what's interesting about this is you can in the lab, you can actually turn on and off these connections. And it turns out that this actuation centers also gets a little bit of input directly from the antennal lobe. And if you want to train flies on something simple like color, or honeybees, for example, you can train them on like blue is rewarded, but green is not. All they need is the antennal lobe for that. But you can also train them on higher order concepts. Like when you see two objects that are the same, you get reward. When you see two objects that are different, you don't. And once you train them on same, you can show them objects they've never seen before, but as long as the two objects are the same, they'll know that that's where they should go and they'll go that direction. That learning requires this. So we know that higher order logic needs this thing, but the simple classification does it all in here. So there's all this really cool architecture stuff going on in here. And the fact that there's these random projections here suggests there's all sorts of theories about sparse coding and things like that. So I've got students in my lab that have been experimenting with novel architectures that play with how you can do this randomness and how with these different ways to do these random projections, you can actually train extremely tiny neural networks to do extremely big things. And so there's, so just getting to this question about are the convolutional neural networks the best thing to put in front? I mean, we don't really know. And this is where kind of the inspiration from biology comes. Biology has come up with this very different way of doing things. Randomization does show up in neural networks, but it's not quite as harnessed as much as we think it is in biology. So that random projections can themselves generate representational spaces that neural networks actually seem to have an easier time learning on than the non-random spaces. So I don't want to spend too much time on it, but I just want to say that there are other structures, outside of the vertebrates that look very much like the feed-forward networks that we build, that we still have a lot to learn from. And because they look so similar to the feed-forward networks that we use in so many different things, we argue that we actually can probably learn more from insects than we can from vertebrates, because the vertebrate brain is like a mess of recurrent connections and things like that, whereas this is an architecture we can wrap our heads around, so to speak. So that's all I kind of wanted to mention about flies and insects or whatever, because it was kind of in the title. But any general questions about this or about how this works or any interest in this? It's fine. If not, just humor me and stare at me, I guess. But this is something that I think is very exciting. Yeah, in fact, this goes further down. This basic architecture, a couple of years back, they sort of reorganized some of the tree of life. And it turns out that insects and crustaceans are extremely closely related. And so now they're all grouped into this new group called the pancrustacean. And the brains of crustaceans and insects, so things with 6 legs versus, there's crustaceans with a lot of different legs, but, lobsters and shrimp and some other things like that, have basically this structure here. There's variations, but this is a general structure that you can see certainly across all insects. You're going to find, again, some of these will be smaller, some will be larger. In social insects, then you see expansions in areas that kind of relate to sociality and smell. But this general structure is pretty much holds. This there's also a visual lobe. So there's basic feature extractors. There's the mushroom body, which everybody thinks is for higher order learning. And then there's these things bolted on the back side of it that actually end up doing the actuation and so on and close the loop. So it's a general structure. All right, see a question online. Yeah, so there's a question on how do you probe these things, and that's kind of a little bit outside of the scope of this class, but at least in the case of the antennal lobe, like reading these codes, you can actually dose this area with a dye that makes it makes a light that a particular type of scope can see. And so you can actually visually see this. So this isn't electrophysiology. It's another type of imaging that allows you to see what's going on. Now, we also can record from different parts of the brain using electrodes and so measuring potentials as they go down these neurons and so on. And so there are people that do that as well. And so we have a project right now that studies sleep in bees, and there's a researcher over in School of Life Sciences who's able to actually record from bees as they're sleeping or as they're awake electrically. So actually record from different parts of the brain by putting probes in and seeing firing rates and seeing how the firing rates change after they learn, after they sleep and learn, if they learn and sleep, and so on and so forth. So, all the stuff you can do with a primate brain, you can do with a bee brain or a fly brain as well. Bees are a little nicer because they're a little bit bigger than flies. But yeah, so a lot of cool stuff you can do with these. All right, so that's one architecture that's a little bit different. Now, getting back to architectures that we actually use in engineering systems. So we talked about the feed-forward networks. What I'd like to move towards is introducing recurrent neural networks. And I'm not going to spend a whole lot of time on this, but I do want you to know that they exist. And in order to get there, I'll mention one other type of neural network, the time delay neural network. In a time delay neural network, you now, instead of assuming that all of all of your nodes, all of your units kind of execute synchronously, then you actually, you think of each unit as acting at a time step where, well, let's just draw it. So like if I take an input X and I go into a layer that I'll call this unit H1, and then so the output of H1 is here, and that'll go to H2. This is output of H1 goes to H2, and that H2 I'll go into an H3. So each one of these you can think of hidden layers, or I guess this last one maybe is an output layer, and that goes to an output. And I can maybe also wire H1 to H3 here. Now, from this perspective, if I just say that this H1 just copies at every time step, just copies the X value at that current time step onto its output and latches it in until the next time step, then, you know, obviously I'll say this, I'll say that H1 at time step K plus 1 is going to be equal to X at time step K. And H2 at time step K plus 1 is going to be equal to H1 at time step K, which, by the way, is equal to X at time step K minus 1. And then I'm going to say that the output Y of K plus 1, I am going to wire it up, its activation function, so that it is a 1 if H1 at time K minus H2 at time K is equal to 0, and a 0 otherwise. And that's equivalent to saying it's a 1 if X K minus 1 is equal to X K minus 2. And 0 otherwise. And so this little, so we refer to this as a time delay neural network, because these neurons, you can kind of view X propagating through them. It takes one time step for X to get from one point to the next, from the next point to the next, and so on. And so because of that, they can be used to find patterns in time. So in this case, this Y will output a 1 if the previous two inputs to the neural network were the same. So if I were to draw the a time, this is K, and I've got this is X of K, I might have, you know, it starts as 1, and then it goes to 0 a few times, goes back up to 1, and then stays 1 for a while, and then goes back down to 0. If I look at the output Y of K, then these two, I'm going to get 3 dots, and then these two are the same, so they will generate a 1 on Y. These two are different, so they'll generate a 0 on Y. These two are the same, and these two are the same, so that will generate a 1 on Y and another 1 on Y. And so we view this as kind of a same detector, where now we're looking for patterns in time. Get out of the way there, patterns in time. So that's one of the things that time delay neural networks do, is they effectively generate a memory where they're latching in old values from the past, so that throughout the network, you actually have values from now as well as values from the past. And so this is related, by the way, to, if we are thinking about convolution filters and all that, this is all related to the so-called finite impulse response filters. And this is just an aside. So that's one thing we can do with time delay neural networks, is we can look for these little finite patterns here. Now, what we also can do is build time delay neural networks that make use of past outputs. And so I can imagine a network that I take X and it runs into, I'm just have this simple output Y, and that loops back to itself as well. So Y takes not only X as an input, but it takes itself as an input as well. And I'm going to say that Y, and I'll call this X of K, and this is Y of K. And so I'm going to say that Y of K plus 1 is equal to 1 if Y of K plus X of K is greater than 0. So I can kind of imagine building a little activation function that's a threshold activation function based on the sum of those two, and 0 otherwise. And what this encodes is the output is 1 if there has ever been a 1 on the input, ever. And so it has sort of an infinite memory. It's not just looking at the past 2 time periods, it's technically looking at all time after that. And it's because it latches it into its own memory. Its output becomes a memory that the event ever happened in the past, even though I don't know exactly when it happened in the past. So regardless of where on my XK, I've had a 1, I've had a 1 anywhere, then on my YK, then it will be a 0 up until that point, and then to the next point, it'll go to a 1, and it'll stay there forever. And so this is another way you can find patterns in signals, is you can actually use the output of the own network as a memory of some far-flung event that happened way in the past. And that way, in a very compact way, like in this previous one, I needed these 3 neurons in order to effectively store the memory of X, because you had sort of X most recently, X in the past, X in the farther back past, and so on. So I've got now 3 copies of X throughout kind of its history. Here, Y sort of stores a persistent memory of all of the X's beforehand, at least in terms of whether this one event has occurred. So this is, as an aside, this is related to the so-called infinite impulse response in filtering. And, but I want to point out here that it's the recurrency creates a very long-term memory. So by feeding an output of a neuron back into itself, you allow yourself to find patterns that are potentially very long-lived. And so with that in mind, and I'll pick up here, we'll finish this off next time, this motivates the idea that, well, maybe if we consider these, these complex multi-layer perceptrons, what would happen if we start feeding layers back to previous layers? And so that falls into our general category of recurrent neural networks, where outputs of the neural network become inputs to other neurons elsewhere in the network, possibly upstream from them. So they can feed back onto themselves. And that allows them to generate novel patterns, chaotic patterns themselves, and it allows them to find very complicated patterns. And so we'll talk about how, like, one of the more famous recurrent neural networks that's used is long short-term memory, LSTM, where up until this new thing called transformers, which is kind of outside the scope of the class, I'm not going to talk about transformers that much, but up until the recent sort of thing with transformers, LSTM was kind of what everybody was using, like in natural language processing and all that. Like whenever you type something into Google, it would try to predict your next word using this LSTM, and it allowed it to give context where it could focus not just on words immediately before the word it was predicting, but on things that you've done way in the past. Like you can say that, wow, this person seems to be interested in sporting goods. So when, I'm going to try to bias my predictions to, if I have ambiguity, to be more about sporting goods than something else. So it can keep track not only of near-term cues, but long-term cues, and that's a so-called long short-term memory. And we'll talk about that a little bit on next time. And the other thing we'll finish up on before we go into non-supervised learning cases is reservoir machines, where this is taken to the extreme, where you take that randomization idea, kind of that I was talking about with the insects, you make it recurrent, so that you actually generate this weird filter that generates like a bunch of these dynamic ripples that you can then learn from. It's kind of like reading tea leaves, but encoded inside a neural network. So, so that's what we've got coming up for us on Thursday. That's all I got for you today. So sorry for keeping you over a minute or two. So of course, if you have any other questions, feel free to come up. I'll also see if there's questions online. I see a question online. Can similar structures provide dynamic models of systems with bursts of controls? Absolutely. In control theory and in systems, in system dynamics, that's what I was mentioning. We've got this thing called an infinite impulse response. So in signal processing, we absolutely are very interested in modeling systems in these ways and building estimators. And so, yeah, I mean, this stuff, this idea of using recurrent memory to find patterns goes way beyond neural networks, and it's sort of a very old idea. So this is sort of the instantiation in neural network form of an old idea. So hope that answers your question. Any other questions online before I end the meeting here? Okay.